Look at, so I have the notes, but under this heading, application of derivatives. Understanding very well that derivatives, we're just talking about first principle, power rule. In fact, in this course, no first principle. So just power rule, quotient rule, product rule, chain rule, implicit differentiation. Though implicit differentiation is being talked about a bit. So which application are we targeting here? Linear approximation. Linear approximations. Which is simply linearization. So we did a bit of some theorems around this, so that now we can talk about its original formula. That linearize is just to get the function, substitute the point, the value of x. Whenever they tell linearize, they tell linearize about certain value of x. So you pick that value of x given, substitute in the function that you are linearizing, and then differentiate that function, substitute the value again, and then subtract that value from x, just like this one. So you can do so many examples here concerning this. Very nice formula. Examples, direct, we just explain. So linearize f of x is equal to the root of 1 plus x about x is equal to 0. So the formula is there. So the first thing here is solution. You can even correct the data. So you say first, I need f of 0, which is the root of 1 plus 0, which is 1. Second, I need f prime of x. Now, you know, we can write f as 1 plus x to the power half, so differentiating it. So we can write f as 1 plus x to the power half. To differentiate it, you have half, and then 1 plus x, and then half minus 1, you get negative half. And then in place chain rule, we differentiate 1 plus x, you get 1, and you multiply, which is the same thing as 1 over 2, because that half is negative, and the half is just a root, so it will be a root in the denominator. As you are collecting data, you also find the f prime of 0, which is 1 over 2, the root of 1, which is 1 over 2. And then you get, well, x minus 0. So, you know, we just have x. Therefore, the linear of this function f, the linear approximation of this function f about x is equal to 0 is equal to f of a, which is 1, plus f prime of a, which is half, multiplied by x minus a, which is x, and that's how you arrive at this linearization. Linearization is very nice because it's something that is used in applications of derivatives. So any function that you bring here. So this was an example A. An example B is f of x. And now there's a variable t. F of t is 1 over t. About t is equal to half. So going there, say, okay, solution, we'll collect data. So say f of half, that will be 1 over half, which is 2. 1, 2, you differentiate the function f prime of t. So you know you could write this as t to the power -1, so that when differentiating, you say negative t -2, which is -1 over t squared. So that f prime of half, so we demarcate. So f prime of half is going to be -1 over half squared, which is -1 over 1 over 4, which is -4. And then x minus a is simply x minus half. So we have corrected the necessary data for us to be able to answer our question. Then now we go and say, okay, so the linear approximation of f about t is equal to half. So this is t. So in fact, I was supposed to use t here also. So it should be t minus a, which is t minus half. This is the information we want. So say the linearization of t is equal to f of half is 2 plus f prime is -4 multiplied by t minus half, which is equal to 2 minus 4 t plus 2. So we get 4, 1 minus t, because we have 4 minus 4t. When you factor out like that, now what else do I here? We go to, I hope I can trace from Daniel to sheet. Should be Taylor sheet. Is it 2? I think it's 2. Okay, Taylor sheet 2. Is it? Not 2. Maybe it's 3. Maybe 3. Try 3. Okay, 3. So 3. We have some questions on the Taylor sheet. This was question 1. So find the linearization of A. So here we said A, B, so we'll just call it C. The linearization of, we'll call it f of x, the root of 4 minus x about x is equal to 0. This was like too direct. Just picked a question almost from the even from the notes. The same x is 0, then just change what is in the root. So you can write this as 4 minus x to the power half. Then differentiate it. You get half 4 minus x minus half. Chain rule, you differentiate the inside of the brackets. So 4 minus x, the derivative is -1. So we'll have -1 over 2, the root of 4 minus x. So the data now, f of 0 is equal to 4 minus 0 in the root, which is equal to +2. F prime of 0 equal to 1 over 2, the root of 4, which is -1 over 4. Because root 4 is 2, so we get 2 by 2. -1 over 4. So the linearization now two plus f prime a. So I have f prime of 0, -1 over 4, x minus 0, which is 2 minus x over 4. D x is equal to 1. So let's start with the derivative. So before we differentiate, maybe we can write our function. We write it as 1 plus x to the power -2. Then we differentiate it. So f prime is -2, 1 plus x, -3 by 1, which is -2 over 1 plus x to the power 3. Then we substitute. F of 1 is 1 over 1 plus 1 square, which is 1 over 4. F prime of 1 so that's -2 over 8. 1/4. Then we linearize. So this will be 1/4 minus 1/4 x minus 1. Then, okay, maybe C is a bit nice. We'll call it E. Cos 2x. So if we call it F, then we'll differentiate it. F prime. Cos is negative sign derivative. 2x chain rule, you multiply by 2. This is the same as negative 2 sine 2x. About x is equal to pi over 3. This is 60. So we collect data. So we say f of pi over 3, that is negative 2 sine 2 pi over 3. Negative 2 sine 2 pi over 3. So what is the angle 2 pi over 3? $120. Yeah, so 120. So that is 60. So what is sine 120? We borrow it from the quadrant. Sine 1, this is 0, 180. So 120 is somewhere here. So this is 120 degrees. So what we do is we use this quadrant. So give angle for 120, which is 180, minus 120, which is 60. Now sine is positive in the first and in the second quadrant. So sine 60. We now go to triangle, which has 60 here. That's 60. Then here it has 30. Then here it has 1. And then here it has 2. And here it has 3. So we're looking for sine 60. So it's going to be sine is opposite over hypotenuse. My root of it over 2, which is equal to negative 3. Now we apply. For example, so now using the equations to use linearization for root of x. I think looks so nice because you get normally this number number 6, that is a perfect square number. So if you put number 6, you can use it to the so in this case, the function of units. Like that. And then since we are talking about 25, so our data, we connect this f of 5, that will be the root of 25, which is plus 5. And then f prime of 25, that will be 1 over 2 root of 25, which is 1 over 10. since we have 2 by 5. So 1 over 10. Linearize. So we say head of x is going to be f of a plus prime of a x minus a, which is going to be f of a, that is 5, plus f of a over 10 minus a is 5. Like this. Then now what is x? Because our target is to linearize, is to approximate the root this time. We don't find value. We don't find the actual value. So we say, okay, approximately the root of 26 is going to be 5 plus 1 over 10, 26 minus 17 minus 25, which is equal to 5 plus 110. So down, then we get 50 plus 1, which is 1 over 10, and this is 0.1. So approximately root 26 is equal to 5. Now this was approximate very, very close, like binomial. So let's see what is the root of 26. Root 26. So root 26 is 5.0990. So if we were to take it, use it on given 26 and then we are given 25. So now this is not given, the root approximate 50. The closest step square to 50 is 9. Then we look at the integration, we will have 49 plus 49 x minus 49. Where we know that the actual is going to be approximately the value of x is equal to that, and then so plus 1 is going to be equal to 27 plus 1 over 14 plus 2 by 7, then 50 minus 49, that's just 1. So here we get 14 up, we have 14 by 7, so 14 by 7, that's 98 plus 1 which is 99. Approximately this is 99 divided by 4, 7.071. So that is a lot. But you check the root of 50. Root of 50. This one is very close. This one is almost exactly the same value. This is 7.0716. So what we're getting here, 29 divided by 40. So it's just some decimals back. But no matter how small error is, you can stabilize it and know where exactly this is supposed to fall in. So log out, go back. So I to do the error analysis. But if you have questions, you can cut this what we're doing. Okay, options, avoid saved.